This week on Monday, we were taking a look at thermochemistry in chapter 5. Our focus this week is really on iterating or taking risks and trying again. So part of the way that we do that is through our think aloud paired problem solving. So when you were thinking about the question from the quiz, the goal was not so much to come to this problem and already know how to solve it, but really to think about your process. So how can you approach pulling information from the problem and then organizing that information in a way that would allow you to make sense of it and then to be able to come up with a strategy for how you would solve this type of problem. So if we think about our approach, one of the first things that we're always going to do, just because it's going to help us make sense of other information, is always to write out our givens. So from this problem, we had several key pieces of information. So one, for example, was our volume. Another one was the number of moles of hydrogen gas. Another was the number of moles of oxygen gas. And then we were given the partial pressure of argon and the temperature. So because of the information that we're given, we know that there are some things that we don't have. We were asked to solve for total pressure in the problem, but we don't have the pressure of our hydrogen gas, and we don't have the pressure of our oxygen gas. That's okay because we have an equation we can use to solve for pressure. And so that equation is our ideal gas law. We're going to rearrange that ideal gas law to solve for pressure. And then we're going to do two separate calculations, a calculation for the pressure of hydrogen gas and a calculation for the pressure of oxygen gas. Now it's really critical that we note that this gas law constant, so 0.08206 liters atmosphere per mole Kelvin, is really important for us to include because that's how we're going to cancel our units to make sure that we get the desired units for pressure of atmospheres. And so when we do this calculation and substitute and solve, we get a pressure of 10 atmospheres for our hydrogen and a pressure of 2 atmospheres for our oxygen. So our total pressure then is the sum of the hydrogen plus the oxygen and the argon. So that total pressure is 14 atmospheres. Now, this would have been a really tricky problem to solve if we hadn't taken the time to write out our givens or to think about how we might rearrange an existing equation to help us isolate and solve for what we were looking for, in this case, our partial pressure. Let's think about this next question. So you were asked to calculate the mole fraction of hydrogen in the flask. So we have an equation for our pressure and mole fraction. So our partial pressure of anything is equal to the mole fraction of anything times the total pressure. And our mole fraction in this case is the number of moles of anything over the total number of moles. So based on the information we have from the problem, we're going to rearrange our existing equation to solve for our mole fraction. So in this case, we have the partial pressure of our gas, which is H2, and we have the pressure total, which we just solved for. So 10 divided by 14 gives us a mole fraction of 0.715, which makes sense. It should be a fraction, so a decimal makes sense to have, and there are no units, so we know that our units cancel, and we did a good job setting up the expression. Before we move on, I want to introduce you to our scientist spotlight for today. So Antonia Coelho Novello is a physician. She started out as a pediatric nephrologist, and she worked for the National Institutes of Health in pediatric care. And then she became the Surgeon General of the United States. So this is an example of the public health service and the individuals that support the health and well-being of the entire United States. She then worked as the Commissioner of Health for New York. And one of the things that she's recognized for contributing to is the Organ Transplantation Procurement Act. And she's also done significant work with the United Nations Children's Fund. She's a great example of a physician and someone who, after pursuing her master's in public health, really made a significant difference in the health and well-being of women and children. So you might be wondering why I always show these science practices, and that's because I want you to see that every time you come to class and engage in learning the material for chemistry, you are doing the work of being a scientist. So you are already scientists. In fact, by asking questions and defining problems, analyzing and interpreting data, by constructing explanations or designing solutions, and by engaging in argument from evidence, you are engaging in science practices. So if we take a look at our learning outcomes for Chapter 5, then the most important learning outcomes that we want to be attentive to is using the first law of thermodynamics and making sure that we can identify the systems versus surroundings and making sense that, as we're thinking about these types of questions, that we think about the direction of energy flow and that we use the correct signs to describe that direction of energy flow. We can convert then between units as well as defining the total internal energy of a system. So the work that we're going to do today, sorry about that. We're going to take a look at two different equations. The energy transfer as heat to or from an object. This is called the heat capacity equation, where Q is heat measured in joules. Delta T is the temperature change, so temperature final minus temperature initial. And then C is the heat that is required to raise the temperature of the object by 1 degree Celsius, or joules per degree Celsius. We're also going to take a look at another equation. This is heat transfer to an amount of an object. So in this case, we're measuring the mass. That's how we get the amount of an object. So Q is equal to M, or mass, times our specific heat capacity. In this case, the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius, or joules per gram degree Celsius. And then again, our change in temperature. And it's important to note here that unlike the ideal gas law where we always had to operate in terms of Kelvin, here you have a choice. You can use degrees Celsius or you can use Kelvin. So these two equations are really important for us to navigate because our choice of equations really matters. So if I'm looking at the following problem, I have a 55-gram block of aluminum initially at 27.5 degrees Celsius, and that absorbs 725 joules of heat. What is the final temperature of the metal? And if I'm given the specific heat capacity of aluminum is 0.903 joules per gram degree Celsius. So here's the really interesting thing. By noticing this specific unit, I know that I'm using the equation for specific heat capacity. So by writing out my givens and noticing this unit specifically, I know which equation I'm supposed to select. Then I can rearrange and solve for my change in temperature, and then substitute and solve for my change in temperature. But I want to be really careful because the equation, or what the problem is asking for in this case, is the final temperature of the metal. So I need to use my change in temperature and isolate my final temperature. So in order to do that, I add my initial temperature to both sides. So my change in temperature plus my initial temperature gives me my total correct answer of 42.1 degrees Celsius. So if I think about the process that I used here, I used mass, I used my initial temperature, I used heat, I used my final temperature, and I used my specific heat capacity. If I think about then substituting in, here's a different way that I could solve this problem. So you'll notice the first approach that I used, I solved for the change in temperature. In this approach, you're solving for temperature final, and you've already done the work to isolate your final temperature from your change in temperature. Either approach will work. It really is about whatever works best for you. So if we take a look at another example, we have a 15-gram block of metal that was originally at 655 degrees Celsius. If we submerge that in 250 grams of room temperature or 25 degrees Celsius water, then the metal and water are going to reach thermal equilibrium. So how do I know when it's reached thermal equilibrium? Well, the temperature is not going to change. So both the metal and the water are now both going to be at 33 degrees Celsius. So assuming that there's no heat transferred to the surroundings, what is the metal's heat capacity? So this is the case where we want to start to think about the transfer of heat. So heat is always transferred from hot to cold. And I've given you one example of where you could place the sign. But I want you to pay particular attention because if we look at how we might solve this problem, you're going to notice that there's a general process that we're going to use. So we're going to list our givens, we're going to select the equation, then we're going to substitute and solve. We're going to check our units and then check our significant figures. This general process can be applied to a great many different types of problems. But what's most important for us is that we pay attention to the signs and what they mean. If you're not certain about this, I would suggest rereading chapter 5.2. That will give you some great insight into heat, transfer of energy, and the way we use signs to help us make sense of that information. But here's the short overview. If we think about our systems and our surroundings, when we sum those two together, we know that because we cannot create or destroy energy, it's only transferred between these two. So whatever happens to our system is going to also impact our surroundings. So that's the reason why we use this negative sign to show that transfer is occurring. So let's think about our problem. If I write out my givens for my metal and my givens for water, and if I think about the fact that I can set up an equation really so that as long as I'm using the negative sign correctly, it's going to help me resolve my math. And I'll show you what we mean by that in just a moment. But in order to do this, I have to write out all of my givens from the problem. And I want to make note of the equations that I'm going to use. In this case, the equation for heat, that includes specific heat capacity, as well as the equation for the change in temperature, or delta T. So we're going to set up our equation and we're going to solve. In order to solve, we're going to isolate how we would solve for our heat for water and how we would isolate to solve for our heat for the metal. Notice you have the ability then to be able to rearrange and solve. So if I wanted to get the specific heat capacity of the metal by itself, I would just divide both sides by the mass of the metal and the change in temperature of the metal. That allows me to isolate the specific heat of the metal. So then if I think about what I substitute in and solve, I'm taking each of my givens from the problem, substituting in, and you'll notice that your units cancel. That's really important and valuable because that allows us to isolate our specific heat capacity units, which are joules per gram degree Celsius. And again, because I'm paying attention to significant figures, I want to make sure that here, the answer that I'm including should be 0.90 joules per gram degrees Celsius. And that's going to be really important because we want to make sure we're using the correct number of sig figs as our final answer. Okay. So let's take a look. Now that we've set up and solved this problem, are there patterns that we can recognize in terms of how we solve this problem? That's going to be really helpful for us as we move forward because there are other types of problems that are similar but slightly different. So when 1.55 grams of hexane combusts in a bomb calorimeter, the temperature rises from 25.87 degrees Celsius to 38.13 degrees Celsius. So we're going to find the total energy of the reaction in kilojoules per mole of hexane. So the calorimeter's heat capacity is 5.73 kilojoules per degree Celsius. So the important piece of information here is that this problem is telling me that I'm transferring heat from combustion to my bomb calorimeter, which is the technique that I use to measure the amount of energy transferred. So I'm going to be able to calculate my change in temperature, which is the information given from the problem. And I'm also going to make use of my heat capacity. Notice the units for heat capacity here are kilojoules per degree Celsius. And then I'm going to substitute both of those in. And remember, because I'm transferring from my reaction to my bomb calorimeter, I want to make sure that I use this negative sign. And that's going to be important because that tells me that this reaction is giving off heat, which makes sense because if I'm doing combustion, one of my products should be heat. So if we think about setup here, then our most important components of setup are that we understand what the units are that we're looking for. We understand that it's a transfer reaction where I'm transferring energy, and we pay attention to choosing the right heat equation that is appropriate for, in this case, our heat capacity. And then we want to make sure that if we're thinking about our change in temperature, that we're accounting for the final temperature minus initial. We're always going to subtract the two in that order. So if we're thinking about then how we might set up this reaction, we are halfway there. So we have our negative 70.25 kilojoules. We still need to calculate moles. So in order to do this, we're going to find the molar mass of hexane. So we can calculate that using our periodic table. And we're going to find moles. And now in order to solve for kilojoules per mole, we're going to place our negative 70.25 kilojoules that we calculated in the original problem in the numerator, and then divide it by 0.017987 moles in the denominator. And that's going to give us the amount in kilojoules per mole of hexane. And so that's going to be a really important way for us to also approach solving these problems, is always to think about them in terms of on a per mole basis. So if we think about, again, this setup, the most critical pieces are that I'm choosing the right equation, and I'm paying attention to my signs, and then that the order of my temperature final minus temperature initial is correct. And then I'm going to complete my calculations here by converting to moles, and then I can use moles to get my final desired units. So why are we learning all this? Well, really, we're interested in the heat of reactions at constant pressure. So I want to know if reactions are endothermic or exothermic. So if the system is gaining energy, then it's going to be endothermic. If it's losing energy, it's going to be exothermic. In class, we talked about how an explosion is something that's exothermic because our delta H is always going to be less than 0, whereas something like ice melting is a great example of something that's endothermic. It's gaining energy from the surroundings. So if we think about everything that we know so far in terms of enthalpy and stoichiometry, we can then do some really cool calculations. So for example, we can calculate what mass of butane in grams is necessary to produce 1.5 times 10 to the third kilojoules of heat. So we can anticipate how much heat we're going to get out of burning a fuel. So if you want practice balancing an equation, this is a great opportunity to do so. This is an example of, again, a combustion reaction. So if we have 1 mole of fuel that reacts to produce negative 2,658 joules, we know that it's an exothermic reaction because of that negative sign. Then we can do our conversion. So we have the amount of energy in kilojoules that's specified in the problem. We have a molar ratio. 1 mole of C4H10 is equivalent to negative 2,658 kilojoules. So this is just like a conversion problem. Then if we know our moles of our C4H10, we can use our molar mass to be able to calculate the amount in terms of grams. And our unit should cancel, so we should be good to go. So if we think about the setup for this problem then, the really critical pieces are that we recognize that energy is being produced and that we can use a molar ratio. If you want help with any of these problems, please check out S Cubed on Mondays, Wednesdays, and Thursdays. Don't forget, we've got discussion this week. We'll be wrapping up thermochemistry, and then take some time to make sure that you reflect on how you want to organize your goals, think about your thinking, and reflect on your learning. We'll wrap up thermochemistry on Wednesday. Thanks again.